is the enthalpy of formation. Okay. Enthalpy of formation is this concept that anything that is willed into formation has an associated energy with it. Okay, so meaning what? Meaning that when I form water or something, I need to have some energy put into that so that water can form. Okay, and the main thing here. So if I have an energy being released for a substance that's being formed, same thing as before, H of the product minus H of the reactant. And the product for anything that's being formed is 1 mole of the substance that's being formed. And the reactants are elements that make up the substance in their most stable form at standard conditions. Ooh, that's a mouthful. So what do I mean by that? All right, so if I want to know how much energy is going to be released when I form water, okay? So let's look here. I have water. Well, how do I make water? Well, I can make water from H and O. But I'm not just going to write H plus O. That's silly. I need to write something that is the most stable form of H and the most stable form of O. At 25 degrees Celsius, the most stable form of H2 is going to be H2 gas. Of H is H2 gas. And the most stable form of oxygen is going to be gaseous oxygen, okay? So that's the definition here, and then I have to balance that, and then that's how I would write the delta H of formation, and I would say that the delta H of formation for water is going to be the delta H. Well, I didn't write that down yet. Here, we'll get to that in a second. So if I have sugar, so this is a product here, sugar, and I want to know how much energy is being released when I form this guy, I need to have look at what's making it up. Well, I have C making it up, I have H making it up, and O making it up. H and O don't exist just like that. It's H2 and O2. And carbon, the most stable form at standard conditions would be C solid. Okay, and this would be the balanced reaction behind that, and the stable form of elements all have delta H of formation of 0, meaning that this has 0 delta H of formation, this has 0 delta H of formation, this has 0 delta H of formation. All right, so let's look at an example here. Oops, that's an example here. So write the appropriate equations corresponding to the standard heat of formation for the following compounds. Okay, so that's the question I have here for you. If I have lead oxide, PbO, solid, I need to write the equation that corresponds to its formation. Okay, so what's making it up? Well, Pb. The most stable form for Pb will be Pb solid, lead, and I need oxygen, gas. That's the most stable form for oxygen, and that will form PbO, and then I want to balance it. Now I'm happy. That's it. If I'm looking now for carbon tetrachloride, okay, liquid. Well, carbon tetrachloride is going to be C graphite. That's the most standard form for carbon. Plus, I need Cl2. That's the most stable form of chlorine. So I have 2 Cl2 gas, and that will form my product that I want. Okay? And let's say I want to do, you can see they're all pretty much similar. If I want to do beryllium hydroxide. Beryllium hydroxide. So again, I have the most stable form for beryllium would be beryllium, just regular beryllium, solid. So you want to make sure that you're writing the correct state. Plus oxygen, plus hydrogen, and that will give me my product, which I didn't write specifically, but that's a solid. Okay, so that's how you do that. That's how you play around with that. So hopefully that makes sense. Just you have to figure out what the most stable form of a compound is. Okay, I can use all this business or the enthalpy of formation to actually calculate the enthalpy of reaction. I can do that, and to do that, I'm using this very disgusting looking equation, which is very easy to use. So all that this says is that I want to add up all the delta H formation of my products and all the delta H formations of my reactants, and I just subtract as it says here. Okay, and I think if we look at an example, this will make more sense. So if I have this 2A plus 3B, that's going to 4C plus 5D, okay? The delta H of reaction would be, okay, I need to look up the delta H information for C, that's a product, and for D, that's a product, and I gotta multiply them by their coefficients. And then I gotta subtract from this delta H formation of A times 2 plus delta H formation of B times 3. Okay? And the only trick with this is that if it's the most stable form for the compound is 0. So if I have oxygen gas being involved anywhere here, I don't count it because it's 0. Nothing was required to create that at room temperature, right? But if it's anything else where it's not like the most stable form of an element, then it's not 0. Okay, and what we'll do is we'll usually give you what we will always give you the data for the delta HO formation so that you can actually meaningfully do this. You obviously don't know this off the top of your head, right? So here, let's look at an example. I have this equation, okay, and I want to know what the delta H of reaction is at room temperature. Okay, and I'm giving you this. I'm going to give you this. Delta H of formation in kilojoules per mole species. I'll give you all of them. LiOH solid is negative 408. This is just here. We're going to refer to it later. Okay, this is for CO2 gas. This is for Li2CO3 solid, and this is H2O liquid. So even though water is the most stable form of water at room temperature, water is not an element. So it has a delta H formation associated with it, which is hard to read. So I'll write that here. That is negative 285.83. That's what this box was supposed to say, but it's too small. Okay, so to get the enthalpy of reaction, easy. Again, it's delta H of reaction is going to be, I need products minus reactants. Products I have as H2O and Li2CO3. They have coefficients of 1, so it will be this times 1 plus this times 1. Okay, so I'm going to write products here. I have 1 times delta H of formation of H2O plus 1 times delta H of formation of Li2CO3. Okay, this stuff is products. Then I subtract from that the reactants. Okay, I have 2 LiOH and 1 CO2. So 2 times delta H of formation of LiOH. Okay, plus 1 CO2, 1 times delta H of formation of CO2. Okay, and that should give me my answer. So I was going to put in the numbers. So these are all given to me at the table, so I'll just throw them all in there. So delta H of reaction, and I'm going to omit all the units, but it's all kilojoules per mole. So it's going to be negative 285.83 minus 278.5 minus 2 times 408, negative 408.3 plus 1 times negative 110.5. And when I add them all up, I get that this is positive 362.7 kilojoules per mole. So that's basically it. The only trick I didn't throw that in here, but if I were to give you a let's say, I'm just gonna write that down without giving you the data. I could have another question like this. Or, maybe I'll give you the data and you can just try it yourself. So if I have CH4 gas plus 2O2, so this is the combustion of methane, and this goes into water plus CO2, both gas. Okay, this is 2. All right, and I want to know delta H of reaction. I might give you here again delta H of formation for each one of them species. Okay, I can have CH4, and this is negative 74.8. Let's say I don't give you O2. And I have water, gas. You'll see it's not the same as the one before because this is gas. Before, the water that I gave you the number was for liquid water. And this is carbon dioxide, and it's negative 393.5. What's that? I didn't give you that. Well, oxygen is the most stable form of oxygen at room temperature, gas. And this is 0. So if I were to solve all this, so if you want to solve it on your own, this ends up being negative 802.34 kilojoules per mole.